So, welcome to session 2. So, in this session, we'll talk about transformation methods and color features. And the two transformation methods we'll talk about are NCDA. So, it stands for Normalized Canonical Discriminant Analysis. And we'll get back to what that means. But basically, it's if you have a known versus another known, you can say class. So, there could be the blue background versus the color of some seeds or pills or whichever samples you have on the belt, on the blue belt. We also have NMAR Nobis, which is a method for defining the difference between known and unknown samples. So again, it could be the known color of the blue background belt versus the unknown color of, well, whatever you put on the belt. And then we'll talk about color features, the standard and advanced features. And after the presentation, we'll show a demonstration on how to create and apply transformations. And then we have exercises as usually. So we'll have an exercise of germinating barley. And this is also what the demonstration is about. So we'll create a classifier that uses MSI color transformation to detect if the barley is germinating or not. And we'll have an exercise on healthy and moldy seeds. And finally on OSR and Chenopodium, where you use some color features to capture the local color variation to separate the two types of seeds. So in general, we have 3 cases. The most used methods are, again, NCDA, NMAR Nobis, and MNF. And we'll not talk about MNF today because mostly NCDA is the one that we use. But MNF is the minimum noise fraction method where, let's say you don't know anything, you want to find differences between 2 unknown classes. And you use an estimate of the noise, so the covariance matrix to do this. But again, in most cases, you will use NCDA and NMAR Nobis, and therefore will focus more on those cases. So NCDA stands for Normalized Canonical Discriminant Analysis, and it enhances the difference between 2 defined classes. And this is visualized in a new transformed image. And as before, the applications are foreground, background. So again, it could be the blue belt versus some seeds on the belt. It could also be on the seed itself. So let's say you have a maize kernel, and you want to find maybe the germinating part of the barley of the barley. You can use that, or a maize kernel. You can find the if one side has a color that is significantly different from the rest, you can use that. You can find a pure sample versus admixture, or healthy versus unhealthy seeds, or any comparison imaginable where you have 2 classes, 2 colors where you want to find a difference between them. And it's a dimensionality reduction method where you go from 19 bands to 1 band. And we go from grayscale to a jet in the range -2 to 2. So you can imagine this case here where we place some vegetables and fruits in this petri dish, and then in red you paint the color of the vegetables and fruits, and in green you paint the background color. Then you train the transformation and you apply it, and what you get is this energy image, is what we call it. And the reason is that so each pixel here will have a value you can see from the heat map. So you see each pixel here will have a value. The blue pixels will have a value around -2 to -1. And the red pixels here, the red regions, will have values around 1 to 2. And the way we can use this image now, this energy image, is that if you want to segment out these parts, you can now say, okay, everything that is above 0 will be foreground, everything below will be background. So you see that makes it easy to get all the samples as foreground, and you can then do further processing to separate them. So Moving on to the in-Mahalanobis method. So in this case, where you have a known sample versus something unknown. So it's a metric for measuring distances or differences in data. So you have a known sample where you have the mean and the covariance matrix, and then you use this to generate some sort of distance measure. And again, the applications could be background versus anything, so the blue belt versus anything on the blue belt, or it could be used for anomaly detection. Let's say you train your transformation on some kind of known color, and you don't want to detect if there's some abnormal color in the seed, then you can use this for detecting this anomaly. And in general, when you only know one class, you would use this method. For example, a seed on some unknown background. If you know the seed color, but you maybe don't know what the color of the background will be, then you could use this method. So the workflow for in-Mahalanobis is similar to NCDA. However, in this case, you only paint with one layer. So here you paint with the blue layer on this carrot. So the goal is to find the color of the carrot versus everything else. And when you then apply the transformation, you get this scaling here, or you get this image here where, and the heat map shows that the values go from 0 to 3. So the distance from the orange color to itself is quite low because the color is blue here. So all these pixels indicate how close these colors are to the orange color. And of course, the color orange, or the color of the carrot, the distance to itself will be quite low. But you see, everything that is not orange colored will have a value of 3 or above. And the reason, so in this case, all the values that could be, let's say 20 or 10, have just been capped at 3. That's why we get this image. However, you can also reset the scale. So now you get this image instead. So here we make the scale between 0 and maximum. So instead of having 0 to 3, you put 0 to maximum. And now the image is quite different. Because in this case, of course, the orange color is close to 0, because the distance to itself must be minimal. However, we see that the distance between this green vegetable color, this green leaf color, is actually closer to the orange color than the color of this broccoli. However, the colors of these, I believe roasted onions and chickpeas, the colors here are closer to orange than the color of green broccoli here. So that's how you can read this image. And again, it's also a dimensionality reduction method. So you go from 19 band to 1 band. And essentially from grayscale to the range from 0 to infinity. So then we pose the question, why are color features even important? Why do we care? And they are used for distinguishing differences in color between classes. So you have these germinating barley seeds where we want to detect this part on the top, this white part. And so the way you do that is you would say this is the foreground color and this is the background color. You apply this transformation, and then you can detect this germinating part here. Same with the defects in French fries. You see this nasty color here. Let's say that we call the healthy part the foreground, and the unhealthy part, the defects, we'll call that the background. Then you can detect those, as you see here. And you can imagine many more applications just like this. So first we talk about standard color features, and those are the ones based on computations that do not use MSI transformations. So we have the CRE all components, and I'll get back to what that means. We also have the spectral mean, the spectral standard deviation, and the spectral coefficient of variation. So spectral mean is simply a feature where you get the mean of every single band. And spectral CV and spectral standard deviation is the standard deviation of every single band and the coefficient of variation of every band. However, if you only want the mean of a single band, then you can use reflectance mean. And going forward, we'll use this data set as you've seen before to explain the different color features. But before that, we'll briefly touch on the CLAP color space. So we are used to RGB, so red, green, blue. Most PNG images are actually in the RGB color space. So you have three values. You have the red value, you have the green value, and the blue value. However, there are also other color spaces in addition to the RGB color space, and one of those is the CLAP color space. And you can see here going from left to right, L stands for lightness, A is the red-green opponent, B is the yellow-blue component, and you can also get other measures such as hue and chroma, but I'll get back to that. So going here on the right, you'll see that instead of RGB again, you still have three values for measuring the color, but now instead you measure the L value, so how white or black a value is. The closer to 100, the more white it is. The closer to 0, the more black it is. And also we measure how green or red a color is. And the more positive the A value is, the more red it is. The more negative the A value, the more green. And same with the yellow-blue components, as you can see here. So imagine now that we only look at the A and B value. So we forget about L. So that's the representation you have down here at the bottom. We only have A and we only have B. Now, given some point, so let's say you have some pixel values, you convert to CLAP, and you look at one point, or maybe you find the mean, for example. This point, if you draw the vector between the origin and this point, you can get the angle between the vector and the horizontal. That will be the hue, and the length of this arrow is the chroma. So that's the two values you have here. So to summarize, you have the L value, you have the A value, the B, the hue, and the chroma. So the lightness, the red-green opponent, and the yellow-blue opponent. And finally the hue, which is the angle in AB space, and the chroma, which is the length of this arrow. And from those values, you get the you can get the mean values of these 5 values and the standard deviation of these. And that's what the CIE all components feature then outputs. For example, let's say we have the three classes again, maize, OSR, wheat. And here I plot the mean A value against the mean B value. So you can see that in this case, the classes are well separated by color. And in this representation, the OSR and maize, they are more red than the OSR seeds. And same for the yellow-blue opponents here. You see the maize, which would say makes sense, are much more yellow than the OSR seeds. You remember OSR, they're quite black. Maize, they're quite bright and yellow. And wheat, they're kind of brownish. So it makes sense that it falls between these two values, 0 to 40. Okay. And again, if you have any questions, just interrupt me. So now advanced color features, they're based on feature transformations. So multispectral imaging transformations. And they have in general more settings that you can play with. And some examples include MSI mean profile, histogram. You can also get the threshold, or you can even use the pixel classifier. And we have some more exercises for that in session 4. But I just mentioned here so you know that it exists. For example, consider the MSI threshold segments feature. So here on the right, you get all the parameters for this feature. And the first 4 parameters, they kind of tell the algorithm where to look in the picture. So here we go from 0 to 100% in the horizontal direction. If you put in 0.5 here, you will essentially cut the image in half, and you would only look at the left half of the image. And you can read more on the manual about these. Maybe I can just show you. So again, if you go to Help, User Manual, Software, and CDT, you can find for CDT there, but you can also find for job feature descriptions. And if you go in here, I think it's one of the very first pages. Yes. For example, this here, you see that when you put in minimum horizontal to 0, maximum horizontal to 1, and so on and so forth for these other values, you get the entire image. But if you put minimum horizontal from 0.2 to maximum 0.8, then you're looking from 20% of the horizontal to 80%, and minimum vertical from 0 to 0.5 will only give you from here to here. Okay. So, and there's also some other parameters, such as the one we call smooth kernel. So if you want to smoothen your image before, like you apply a filter, you can do that. The threshold comparison method is basically where you pick a threshold and you ask each pixel, is it greater than 0? Then it's put into the foreground. So what happened up here, if you look in the upper right, is that we apply a transformation, and then you get this image here. So here you basically applied a greater than with 0, and then applying the transformation only to this seed. We ask each pixel, so is the pixel above 0 or no? And if it's above 0, you see then we get the fourth image over here. So all the pixels that were above 0 are put into the foreground class. And most importantly, you have to apply this transformation here. So you make the transformation and you put it into this feature here. But I will get back to that in the demonstration. Furthermore, you can also apply post-processing. So let's say you get segments like these. Some of them might be quite large, some of them might be quite small, like these trailing segments. You can then say, okay, I want my segments to be at minimum 0.3 millimeter squared in size. And that means we will move these small these small segments here, and only retain the big one, the big segment which we actually care about. In the next 10 slides, I'll show you MSI mean and MSI threshold and reflectance mean. So the workflow is again that let's say you want to find a difference in color between maize and OSR. You paint the maize with red here and OSR with green. And what you get are the energy images as you see here on the right. So you see that the maize, each pixel clearly has a value above 1, between 1 and 2. And the OSR has values around the -2 and 1. So they're well separated. And you could then apply the feature called MSI mean, where you have provided the transformation to the feature. And now you compute, so you apply the transformation, and then you compute the mean value of the entire energy image. And what you get for maize, you can see here, they hover around 0.8, which makes sense. And OSR hover around -1. And again, you see they are well separated. So these questions we pose over here, is the transformation good at solving the problem? And it clearly is, because they are, again, well separated. There's no overlap between the populations. So we would expect a classifier to give perfect results with these features. Moving on to MSI threshold. Again, you apply the same transformation of Maze and OSR. And now you apply the segmentation after applying a threshold of 0. And then the results you get are the ones on the right here. So since almost every pixel of Maze in this energy image will be above 0, you get the entire blob. But in this case, for the OSR, you see that all the pixels are below 0, so you get nothing essentially. And so plotting the MSI mean against the MSI threshold, you see that almost none of the pixels of the OSR seeds have any response for maze color, while you see the maze colors, almost 100% of them have the color we're looking for. And then we can, so NCDA is only defined for 2 classes. And if you want more classes, then we could apply the pixel classifier. So in this case, we have more than 2 classes. Again, Maze, the OSR, the wheat kernels. You apply the 3 layers and train the algorithm. And you can then use the MSI pixel classifier area feature. So since we have 3 classes, we get 3 numbers out. And you can, without knowing the name here, you can kind of deduce what the feature does. So if you look at the x-axis, you see that all the maze kernels are nicely distributed around 0.9, while you see there's no response at all from wheat and OSR. So this feature measures how much or the proportion of maze color in a blob. And the feature on the y-axis in the same way measures the proportion of OSR color. And you see there's almost no response from the wheat and from maze, but all the pixels of OSR, they are belonging to that class. And finally, the last 3 slides, we'll talk about reflectance mean. So in the software, you can open a blob, you could paint on it, and then you could open the image to statistics tool. And you get this tool out where you can choose the mean. And you see here, you get the mean of every single band. And if you use the reflectance mean feature, so here I chose the blue, the green, the red wavelengths. And I also have the image here from VMware Lab, so you can cross-reference to check that you get the same values. So this feature allows you to get the mean value of specific bands. Again, you can use spectral means to get the mean of all the bands. But if you don't want that, and you only want the mean for specific bands, then you can use this feature. And to round off, in this case, I plot the reflectance mean blue of 470 nanometers against the red 645 nanometers. And you see that in this representation, Maze is much more red than the OSR seeds, and is also much more blue, has more blue response than the OSR. And again, they are, you can see, well separated. And that's the slideshow. So if there's no questions, then we'll move on to the demonstration. You can ask too if you want. Yeah. Hmm? Let me just go back to, maybe is it this slide you're talking about this one? Is that what you're asking about? Okay. Yes. Yeah. You mean the pixel classifier or which one? Sorry, did you mean?
I need to summarize the questions. Maybe
Yeah.
I missed the things. Sorry about that. Yes,
Okay.
because a question about the blob function, but you described the CDT, especially color picture.
Okay.
So I mixed the two things. So maybe
Okay. Maybe when you see it in action, maybe it makes more sense. Or so are you asking specifically about the feature or
yeah, it's about the blob function.
okay.
Forget about the color picture and the CDT. Yeah.
Okay.
When we need to predict the germination test with the blob function. At
Okay.
that
Okay.
time, so how about the way I usually the make the area with the whole grain. Maybe if
Okay. Okay. Yes.
the grain the
Yes.
short
Okay.
area
Okay.
instead of the whole grain, maybe the prediction of the germination could be increased or not. So I just
Yes. Okay.
questioned.
I think I understand your question. And correct me if I'm wrong. So you make two transformations. The first is to get the grain from the belt, and the second transformation is where you go from here to the third image. So where you look only at the seed, you only paint on the seed.
Yeah,
Does that answer? Is that? Yes,
yeah.
exactly.
After segregation.
Exactly. You do segmentation first, and then you do the other transformation. Exactly.
If we do
Was that the question?
yeah, if
Yes.
you do that if you make the area, maybe we assigned the class as the germination, non-germination.
Yes.
At that time, so we
Exactly.
usually point the whole grain. I usually do that. Maybe
Okay.
instead of the point the whole grain, how about the extracting the sport area instead of the whole grain? How about this one?
And
It's good.
exactly.
It's
And
better than the existing my method or not? Just
but
question.
that's it. Exactly, and you're right. That's exactly what we're actually gonna do now. So we segment the entire grain, and then we only look at the top part to find that.
So when we use the blob function, how about that? Between the whole grain and some part of the grain, which
Yes.
method is better? I just question.
Okay. I would say the MSI threshold feature. So if you use MSI mean, you get the mean of the entire seed. And if the germinating top part is very small, it's very difficult to measure. But if you use thresholds, the one you use here on the top right, you see you can find this small part and you can measure it. So I would use that's also in the exercise.
I see. I understand. Thank you.
So that's okay. I hope it answered the questions.
Yeah, go ahead, please.
Okay, thank you. Very good question. If no one else has more questions, then we go to the demonstration. Okay, so let's go to CDT. And so here I will, so again, you can, if you want, you can follow me or you can watch what I'm doing. It's up to you. So if you choose barley germination train, we have this data set where, let me just make it bigger. You see, we have two classes here. So we have the germinated class and the not germinated. And you see all the seeds where you see you have this top white part, they are germinated. So if I open this Blobber Vitameer lab and this non-germinated one, you see that the germinated part at the top here makes this one germinated, and this one has no germinated part. So what we do is then we paint this top part here, the germinating part, against the color of the seed here. And after doing that, we choose transformation builder and create this transformation. And as mentioned last time, so the most important part is that the values down here in this lower right-hand graph, if it's above 3, then we're good to go. Then it's a very good transformation. So if I apply here, you see that of these two images, nothing is detected on the right, as it should be, because it's a non-germinated seed. But we see that we detect exactly the germinating part of this seed. So what we can do now is we save this transformation. So we could call it germination versus background, or versus non-germinated. And what we do is then we go back to CDT. And here you would right-click and add feature. And in this case, I would advise using the MSI threshold feature. And we can use the more advanced one called MSI threshold segments. And in this case, so you see here are the parameters I showed you before on the slide, where you can choose to look at the entire seed. And the most important parameter is then to choose the transformation itself. In this case, you choose germination versus non-germinated. And the next step is then to calculate the features on the blobs on the node. And again, as last time, you can go to view feature statistics. And you can get a histogram of the distributions. Actually, let's go to so in this case, you see that the feature doesn't work that well because we only train on 2 seeds. And again, this is a very common occurrence. Initially you train the transformation, and then you'll find some cases where it doesn't work, and then you'll iterate until you get a perfect feature. So here I would choose some of the seeds where we found some signal. So here on the left, clearly we have a seed which is germinated, and we can just confirm it by going back. So in this case, if we apply, we find nothing. So in this case, we would go in and we would paint that part of the seed like this, and the other part green. And here the transformation actually works quite well, but maybe if we zoom into the border, we see that it's because of the borders that we actually get some signal. So if we train this transformation again, you see now the eigenvalue drops, but it's still significantly above 3. But we apply this. So you see now we get some more signals on the borders, and there's two ways to remedy this. Either we can choose a margin, so we only look at the inside and see it, or we train the transformation more. Let's try and go ahead with the transformation we have. So let's save this again. And in this case, we actually get a very good separation, but we could improve it even more. In cases like this, we find a little signal, and here we find some signal maybe from the background. So we could increase the margin by a few pixels. And we see we get an even better result. So again, we could continue in this manner to get a perfect transformation, but this is the general idea, so we'll stop at this point. So if there's no more questions, then we'll go to exercises.
Actually, I don't have the questions about your instruction, but I'd like to propose your instruction way to make the short and especially because the attendance is very limited. So actually, I pre-studied your section 2 before your instruction. So, but I'm not familiar with the function key in the software.
Yeah.
So I recommend you to please show us the exercise shortly. If you give the times enough times, but maybe it's the only 3 people attended here. So to make your training is especially, I hope to how about show the exercise shortly, maybe within the 5 minutes or 6 minutes, and then I memorized your way, and after the training I just follow your way, and then maybe understand what is your intention and why to make the more impression, and then maybe I have the questions about why or make the more way. So that's my proposal. How about that?
So you want to exercise first, or?
Yeah, I mean after your presentation, and then
Yes.
maybe you will give the times that we need to practice with the exercise. But instead of that, I recommended you to just show us the exercise protocol, blah blah blah, like this.
Okay. But the thing is, in my opinion, it's also good that you do it yourself, because I could show everything, but then people might not remember. So it's also good you can follow the instructions of the exercises to remember it.
Yeah, but
Because
please ask another attendance. That's my opinion.
Okay.
Yeah.
So, but if you follow this exercise here,
Yeah, okay.
it's exactly the same as what I just showed.
Okay.
So you see, this exercise 1 is exactly where you use the same data set and you paint these kernels. You use this feature, and then you get this result. So it's exactly the same as I just demonstrated.
Actually, before attending this section 2, I pre-studied the exercise, but between the standards, I don't understand which one. Maybe I'm not familiar with the function of the software. So I just recommended you. Please understand.
If if there's anything the exercise that doesn't make sense, we would very much like to know it. We try to make it as understandable, but maybe there's something that's confusing or maybe doesn't make sense. So we would very much like to know if anything is can be improved.
Okay, I think please just show me the exercise 1 in advance, and then the exercise 2, 3 is the homework, and then next in when we attended the section 3, at that time whenever we have the question about the exercise in the section 2, at that time you can show us the how to do that. How about that?
So you want me to show the exercise or how?
Just show me the exercise 1 in section 2. And then
okay,
exercise 2, 3 is just the homework. How about that?
Yes, but that's actually already what we did here, because exercise 1 is actually what I just showed. So it's the same data, it's the same classes.
Ah, really?
So you see what I just showed now, you will do now in the exercise. You see, you do exactly the same as I did. You use the same data set. You use maybe I can zoom in. You do the same transformation. So what I just showed now is what you do in the exercise. Actually.
Yeah, that's right. Maybe I have the troubles in the exercise 2, so I
Okay.
skipped to do that.
But okay. But if you have troubles there, then you can share your screen and I can answer questions.
But I just follow up your instructions, and then I wanted to do it myself, because sometimes it's take time consuming protocol or procedure. I guess so.
Okay. What I recommend is maybe you do, if you already did exercise 1, you can do exercise 2.
Yeah.
And if you have questions now, then you can share the screen.
I just mentioned the exercise 1, 2 I pre-studied, but I didn't finish the do that. So I just want to know how you to do exercise 2, and then I'd like to get your tip.
Okay. I mean, we can. Let's see here. So open black mold and healthy kernels. Okay, so the next step is to the next step is we copy all of them into an empty classification model. Okay. And see what's the next step. So the next step is to go to this classification model and right-click on the root and select Show Blobs and Node. And next step, remove the predicted unknown class from all blobs. And okay. And select 3 to 4 molded seeds and open them in VMware Lab. So we can right click and select some black mold. Let's choose this one and this one. And let's see, the next step is then okay. Let's see what the next. So step 6 is then we have to create an Mahalanobis transformation. Okay. So we select up here N Mahalanobis, and then we make sure all the images are selected, and we calculate. Let's see, apply one of the images. And then we get this case. So, and if we do not get these results, go to step 8. So we see that these do not look like this. So let's see, the range should be changed. So we go in and scale settings, and you get this window. I believe is the same. Yes, this one. And they tell you to stretch to fixed value range. So this one, and let's see, from 0 to 3. So we go from 0 to 3. And then they tell you to okay, I might be missing some instruction here, but the last thing you do here is then to you can apply a color bar, and view mode, we change this to jet. And then in, let's see here. Okay. So we could now choose a healthy kernel, something like this, and then apply the transformation. And jet. And this one, let's just double check. I believe it should have the same. No, it doesn't. Now it has this scaling here. So the exercise asks you to find the differences between the healthy and molded seeds. And now what you see is that so we're looking for these cold areas or these blue areas. So because we painted the moldy areas, we expect on the moldy seeds to get spots like these. But on a healthy seed, like this one, we expect to see no mold at all, so no blue spots. And that's exactly what we get here. So let's see what else. Okay, we did all this. Save the transformation. And go back to CDT and add the MSI threshold feature. So on the right here, we right click and add MSI threshold. And okay. And what else? So they tell us to set up the feature so that it corresponds to this image here. So maybe we can put the exercise on the left and the CDT on the right. So if we look here, we see that we put in a threshold of 1.5. Let's choose pixels and then the transformation. What else? Okay. All right, and that's the exercise. But what we could do is we could calculate features on blobs and node.
Yeah, great. Actually, I have a trouble in step 8.
In step 8.
Yeah.
Okay.
Yeah, after your instruction, I understand fully.
Okay. I can see maybe we did miss. Thank you for bringing that up. We did miss, I think, the step with putting in jet. Okay. But now it makes sense, or?
Yeah, I understand
Okay.
I guess I could follow your instruction fully.
Okay.
Thank you.
Good. Yeah, of course. Thank you. I'm glad to hear that.
Yeah. To be honestly, I studied section 1 exercise. I did solve all of the question problem. So,
Okay.
thanks to your instruction, maybe next in the section 3, I will try to solve the exercise in section 2, and then maybe at that time I have the trouble again. I will ask you again.
Yeah, of course, of course. So what you can do now is you can try and do exercise 3, and then if you have questions, you can ask them.
No, I think you need to focus on other jobs. Maybe I hope you need to make the training course efficiently. I don't
yes,
like
but
finish it this time.
Yes, but at this moment we have 30 minutes, so you can do exercises. You and Terra International can do exercises, and if you have questions, we can answer them. And if you do not finish, then we can always take the questions next time if we have no. Yeah.
Okay, I see.
Okay.
Okay.
Do you have more questions we should answer now, or?
Now I don't have questions right now.
Okay. Great. Then but you didn't do exercise 3 yet, or?
I think I need the times about the exercise about the exercise 3. Now I don't have the times right now, so yeah, maybe I will try the exercise 3 before section 3 in your instructions at that time. So.
Okay, that sounds good.
Yeah. Okay.
Okay, so I will stop sharing.
Thank you so much.
All right.
Yeah.
Okay, so see you, Damien.
Yeah, see you.
How about you, Tara? Are you doing well?
Hello.
Hello.
Yeah, we followed through the exercises 1 and 2, and we are yet to try the second one ourselves. So we will and workspace to check the debug image. I've shared my screen, but I couldn't look at the workspace.
Okay, yeah, okay, we need to update that. What you can do instead, you can go to, if you close this view and go to File and Workspace Manager, and then find CDT course. And then you can, on the right, you can open an Explorer. On the right, yeah. And images. And wait, can you just go, sorry, can you go back to VMware Lab?
Yeah.
Just to see. Okay, did you apply the debug image yet?
Yeah.
Okay. Okay. I think your version is an older version. So if you go back to File Explorer, yes, and on the left, if you scroll all the way up to Documents, yeah, exactly, and find Videometer and Videometer Lab, and then Images. They should be in here.
Oh, this one.
Yeah. So also, I do recommend that you update to the newest version of the software, because in this version, the debug images were saved in the default workspace.
Okay.
In the new version, it saves them in your current workspace.
Okay, understood. Thank you.
Yeah, no problem. They do, yeah.
Okay. I was actually looking for trying to find the one that device, and it's saving the another one, but it overlaps.
Yeah, unfortunately. Yeah.
Okay. So it's basically saves the background of whatever features we've applied, right?
Exactly. Yeah.
Okay. I think we're done with the exercises as well.
Okay, you're done with all three?
Yeah.
Okay. Do we have any more questions, or maybe do you want to end the session here?
No, we don't have questions at the moment.
Okay. So it's up to you. You can use the remaining 15 minutes, or you can get off early. Yeah. Oh, yes, please. Yeah. Yeah, I see your screen. Yeah. Yeah. So you remember from the first session, I showed a slide where you can make a model where it has more nodes. Here you only have one node, so the difference between node and branch, there's no difference. But maybe let's say you make let's say at the Chenopodium child node, let's say you make one more node. So let's say maybe you make like an apple stone classifier, also fruit stone classifier. So first you get as fruit, and then there you say apple orange. That would be 2 nodes you have. If you train nodes, you only train the top node. If you train branch, you train the node and then the second node. So when you have deeper models, training branch will train all of the nodes, but train node will only train the one node you are in at the moment. Oh, no problem.